Thank you for this opportunity. I want to share with you some of the work I'm doing with Dr. Rosemary Harris at UCL. I'm her PhD student, and our work is now on archive, and it's now under review on JSTAT. Uh, so let me start at a very familiar point. This continuous time random walker, which is completely memoryless. That means the waiting time distribution at each site is exponentially distributed, and then the rates of jumps out of the site are constants. If you like, even the transition probabilities outside of the sites are constant. So if these rates are not equal, then this system would be out of equilibrium. And then, as good statistical physicists, we can ask what is the long time average current in this system. Current meaning the total number of particle jumps forward minus the total number of particles jumps backward. So it is easy to see that the mean of this quantity would just be the forward rate minus the backward rate. So if you want to go beyond the mean, let's say if you want to know the rare currents, you have to use the large deviation theorem. So it's now typical to use that. So this will tell you the probability of certain currents decays with this exponential type of law, which is governed by the rate function I of j. So in general, this I of j is pretty hard to calculate directly. So there's an indirect way to calculate it through this quantity called the scale cumulative generating function that characterizes the fluctuations in the system. So all you do is if you can calculate this SCGF, there's a nice LF transform between the SCGF and rate function. So if you can calculate SCGF, then you can calculate the rate function. This is basic large deviation theorem. So for this simple case, you can just do some spectral analysis and you can get the result analytically. But if more difficult cases, however, you have to use some kind of numerical methods. So I want to focus on a particular numerical method using machine learning, which was proposed by the Garahan group in Nottingham by one of his postdocs, Dominic Rose. What Dominic did is he constructed this kind of a reward structure, which when optimized, will saturate this bound, which will give you the SCGF. So if you look at the sigma theta bit, that is called the control dynamic. So in fact, if you control this theta, the goal is to optimize this control dynamic so that you optimize this entire thing to get the SCGF. So this is in the Markovian case. So this bound is well known. So we will want to extend this to non-Markov cases when at least the theta is a variational parameter that you can vary while doing so. So this is kind of optimal control problems can be solved using reinforcement learning. In fact, that's a machine learning paradigm very specifically designed for doing problems like this, solving problems like this. So now let me introduce memory a little quickly. I'll take the same example and I will focus on a very specific class of memory called the semi-Markov memory, where I just replace this waiting time, which was exponential in the previous case, with a non-exponential distribution, such that now all the rates are now dependent on the waiting time. And also the transition probabilities, of course, because the transition probabilities are also now dependent on how long the particle waits. So here, you have to go numerical, you have to calculate the SCGF numerically because analytical techniques, except for very special cases, it's not really possible. So let me just jump right ahead and see how to extend Dominic's framework to semi-Markov systems. So what we did is we just extended the state space to include the waiting times of the system. And then we formulated a new reinforcement learning problem in this extended space. That would actually and then that would require constructing this new reward structure with two controllers instead of just one. So you would need two controllers, one for the waiting time and one for the jumps, so to handle this extended state space. And after taking some assumptions on the extended space pertaining to ergodicity, these two conditions, which we can discuss, we can construct a reinforcement learning problem on this extended state space. So once we construct this, then we apply the standard actor-critic framework, which is a multi-agent setting, to learn the two controllers. The thing here now, the key part here now, I don't want to go in very detail because it's a statistical physics conference. I don't want to go in detail on the machine learning part, but I just want to mention that we need two controllers here because, two controllers, for two controllers, we do need two neural networks. And we are learning very complicated densities. That's why we need neural networks. So here's the promised result for the SCGF of the random walk example that I just gave with gamma distributed waiting times, not exponential. So if for gamma distribution, somehow you can calculate an analytical result. And you can see the reinforcement learning matches pretty well with the analytical result. So this is what the whole problem is. Now I'll use the rest of the talk to show you some more examples on more interesting systems where we applied our method. So here is some kind of a run and tumble thing, particle which we discussed, or you can also look at it as a reset. But here the particle just goes in one direction for some time, tumbles and goes in the opposite direction. Or you can think of it as a reset to a new direction, not to a previous point. So we heard of resetting and run and tumbles a lot. But the only thing is the waiting time in the forward directions and the waiting times in the backward direction are from different distributions. This has a very interesting physics, but I will not discuss the physics now because it's in preparation in another paper. But I will show you, I'm just showing the large deviation plots for SCGS, and you can see the method works well here for purposes of this talk. Here's a more, again, multi-particle example, two-side TASEP with where all jumps are gamma distributed. So it's an open system, so particles can jump in. And here there are some complications with competing clocks and all that. But even in this case, you can see that the SCGF matches pretty well with the clocks. So SCGF from the reinforcement learning matches pretty well with the analytics. And as a final example, we have this multi-site case with all the arrivals which are gamma distributed waiting time, and everything else have exponential distributions. And then you can see that we have some good matches for small systems, and we were able to go all the way to the site size of lattice size of 64, which is well beyond the SCGF calculations you can do with exact diagonalization methods. So it requires some more complications with machine learning, but it still can be done. So it's a demonstration of that. So just to conclude my talk, I just wanted to convince you that neural networks are really good for the future of non-equilibrium studies with some benchmarking comparisons and stuff which are more mechanical in nature. We hope that in future we can discover some new physics with neural networks in the field of non-equilibrium statistics. Thank you so much.
Thank you for the talk. We have time for a couple of questions.
Yeah, thanks for the nice talk. Could you go back to the gamma TASEP? I was not sure I understand the rules.
This one or this one? This one. Let's fix on this one.
I didn't understand the difference either between the two.
Here there are two sites.
Oh, there's just two sides.
Just two sides with open boundaries.
Yeah.
But every single jump is a gamma distribution.
Fine.
It has a gamma waiting time distribution for every single jump. So here there's some, but the complication is in this third bit where there is a clock competition here, which happens, and we have to take care of that.
But why
in this part, only the arrivals are gamma distributed. Have a gamma.
Everything else is
exponential.
Okay.
So we can check for 64 sites also. We can check the results. It's well beyond.
What are your probabilities? I mean, once the clock rings, what are the probabilities? I mean, your gamma.
Yes. In this one, the probability, the waiting time distribution, would be given by the gamma distribution and the survival of.
No, I understand the waiting time distribution, but what happens to the probabilities? I mean, are you still doing jumps with
We have to
probabilities?
calculate the probabilities from the waiting times. So you can get the probabilities from the waiting times.
I see. Okay.
So you'll automatically, the system actually does it. Here it is for the SEGF. In the original system as well, we can do this. So.
Okay, thanks.
Any other questions? If not, we'll thank the speaker.